In Lesson 10.3, you're going to be learning about mean absolute deviation. And you'll be able to find the mean absolute deviation of a set of data, and you'll also be able to compare the mean absolute deviations for two sets of data. Remember that the essential question for Chapter 10 is how are statistics used to draw inferences about and compare populations. In the middle of page 447, you have the definition of mean absolute deviation. The mean absolute deviation is the average distance between each data value and the mean. So in order to find the mean absolute deviation, we're going to first of all have to calculate the mean, and then we're going to have to find out how far each data point is from that mean, and then we're going to find the average of those distances. Example 1 shows you a step-by-step process, and you might need to watch this first and listen and then go back and re-watch and write it down. Or if you want to do it along with me, you can. Just know that there are several steps, and it's going to be important that you understand how to do this process. Step number 1 when finding the mean absolute deviation is to find the mean. So on number 1 here, got it, you have the number of tomatoes in 5 boxes, and there's the 5 numbers right here. So notice step number 1 is that I took 18 plus 21 plus 16 plus 19 plus 20 and divided it by 5. 94 divided by 5 is 18.8. That's the first step when you're calculating mean absolute deviation. So once I know that mean, I'm going to take each number, 18, 21, 16, 19, and 20, each number in the original data set right down here, and I'm going to subtract this number that I just found in the first step. So 18 minus 18.8, 21 minus 18.8, 16 minus 18.8, 19 minus 18.8, and then 20 minus 18.8. And then all of those differences are going to be averaged together. So you notice that I added them all up and I got 7.2, and then I divided by 5 and got an answer of 1.44. So to describe what that means, you would say the average number of tomatoes per box differs from the mean by 1.44. Again, it was a lot faster explaining it because I wrote out all my steps and I showed my work. Make sure you have all of those steps on your notebook sheet so you can refer back to them when calculating the mean absolute deviation. Moving on to example 2 on page 448, you're going to be comparing variation with two data sets. Notice right here it says a data set with a greater mean absolute deviation has data values that are more spread out than the one with the smaller mean absolute deviation. So that's an important concept right there to keep in mind. So in example 2, we have two sets of data, and so what we're going to have to do is we're going to find the mean of both, and then we're going to subtract the mean from each data point, and then we're going to find the average of those means. Again, it's a step-by-step process, and as long as you show your work, you should be okay. For this problem right here, I already have some things written out for you. Over here on the right, I have the low temperatures. So notice I took these little dots on the graph there, and I translated those to the numbers, 44, 48, 48, 49, 49, 50, and 52. Together that added up to 341. Divided by 7 data points, so the mean is 48.71. Notice then that I took each one of these data points minus 48.71, and I got these values right here. Once I got those values, I added them all up and then got 12.29, and then I divided it by 7 because there's 7 data points. And my mean absolute deviation for the low temperatures was 1.76. Same thing on the high temperatures. I translated each of these dots to numbers in a row right here. I added up all of those numbers to get 548 divided by 7 data points to get my mean of 78.29. Take each one of these data points minus 78.29. And remember, it's the absolute value, so we're just doing the positive value of whatever that answer is. So I got 10.9, 4.29, 2.29, 0.29, 4.71, 5.71, 6.71. When I added those together, I got 34.29 divided by 7 is 4.90 mean absolute deviation for the high temperatures. My final answer, the mean absolute deviation for the low temperatures is less than that of the high temperatures. Okay, 1.76 is definitely lower than 4.90. And remember what that meant up here at the top. A greater mean absolute value means that the data are more spread out from the mean of a data set with a smaller mean absolute deviation. And so I added one more sentence to my description. The data for the low temps are closer together. Again, this isn't a hard concept, but remembering the steps can be a little overwhelming. So make sure that you have these examples down in your book. You have a few more problems to do from this lesson that are not related to mean absolute deviation. Over on page 451, you're identifying the slope and the y-intercept of the graph for each equation. There's a spot on your note sheet to record both of those items. And just a refresher, the slope is the coefficient of the x. So in this case, the slope is -3, and there's no y-intercept. The slope is in what's in front here of the x, so this would be 1/5 for my slope, and my y-intercept is 5. Notice that you have y equals -0.5, and there's no x value, so we are going to have a horizontal line, and a horizontal line has a 0 slope, and it crosses the y-axis at that point right there, so -0.5. Finally, on number 25, this is not in slope-intercept, and so you want to subtract 2x from both sides to get 3y equals -2x plus 60, and then divide by 3, y equals -2/3 x plus 20. Now you have your slope and your y-intercept. There's an ed puzzle for this lesson, and there's also a homework sheet and a problem-solving sheet. Let me know if you have any questions.